Good morning, student. Welcome to the Physics Major second semester class. In the last few lecture, we have explained the superposition of different kind of simple harmonic motion. For example, in the first lecture, I have defined or I have derived the superposition due to two simple harmonic motion traveling in the same direction. After that, I have derived the superposition of two simple harmonic motion having different frequency. Earlier case was equal frequency and the second case was different frequency, and thereafter I have derived the superposition due to two simple harmonic motion in two mutually perpendicular direction. Okay, so in this class I am going to derive the expression of superposition due to a n number of simple harmonic vibration having equal amplitude and equal successive phase differences. Okay, so this topic will be superposition of n SHM simple harmonic oscillation having equal amplitude of each of the SHMs are same, but they have successive phase differences. Okay, so this will be our topic today, successive phase differences. Okay, so this derivation is actually very important for interference and diffraction pattern. When I will teach you about the diffraction and interference of light, then this topic will be very, very useful. Okay, so you have to keep that thing in the mind. So let me define. Say first simple harmonic oscillation is A naught cos omega naught into t. Okay, so second will be, you see, equal amplitude but successive equal phase differences. Right? So A naught cos omega naught into t plus phi naught. Okay, so x3 will be equal to how much? A naught cos omega naught into t plus 2 into phi naught. Okay, so phase difference is between this and this is phi naught, between this and this is phi naught again. Okay, so in this way the nth number of simple harmonic oscillation xmt will be equal to A naught cos omega naught into t plus n minus 1 into phi naught. Okay, so this will be the nth number of simple harmonic oscillation. Okay, so according to the superposition principle, the resultant oscillation will be now xt. We have to just sum up all those things. Okay, I is equal to 1 to n xn t. Okay, so this is we basically have to do the summation. Okay, so if we take A naught as common, then it will be cos omega naught into t plus cos omega naught into t plus phi naught plus dot 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 plus cos omega naught into t plus n minus 1 into phi naught. Right? So this will be our final expression for order resultant amplitude. Okay, so you see, this derivation actually we can do by two different types of way. The one which I am doing is an analytical derivation, and there is also a graphical derivation is possible. The graphical derivation is little bit difficult, but it's much more insightful. Okay, now we are going to derive it analytically. Now when we have to do the summation of this kind of series, it's very useful to use the complex notation. Complex numbers, they are actually known as the jewels of mathematics. Okay, so to sum up this kind of series, complex number is the best practice to do. So what I am going to do, I am going to write this expression in the form of a complex number. Okay, so how can I write it? Suppose I write z1 as z1 is a complex number. I can write it, say, x naught exponential I into omega naught into t. Okay, let's suppose I write it like this. Then what will be the real part of this expression? This is a complex number, right? It will have a